We're going to begin now with a historical view of how the modern views of the atom came about. Not only do I want you to get an idea of what the history is, but also it's a nice illustration about how science goes about formulating or putting together complex models of how the world works. The quote from Ernest Rutherford, which is one of the people we'll talk about, really kind of captures the idea of how science is done. And you'll notice that scientists are not dependent on the ideas of a single person, but it is a combination, a culmination of thousands of people. And they're all trying to solve, in this case, the same problem. And each makes a contribution in certain areas. And what happens is that gradually a very large structure of knowledge or understanding gets erected or built. And how that process takes place is called the scientific method. So how does it kind of take place? First, a given individual creates a tentative explanation of known observations. And it's very important to realize that these explanations that are generated in science are testable. They can be subjected to the experimental work. The experiments themselves, what they do is they look at the observable information, and the key word here is prediction. Experiments check predictions that are made by a hypothesis. It generates a testable set of possibilities that should happen if the hypothesis or theory is accurate. Now, after a very extensive number of experiments by many people, the explanation becomes a law. And it's a concise verbal or mathematical statement, and it describes a relationship that always takes place under the same conditions. What that means is you should see the same effect every time. For example, plate tectonics predicts a number of things about mountains and earthquakes and stuff like that. And if you look everywhere in the world, you should see these same events happening. Of course, you do. So that's the sequence of events that takes place in the development of these complex models or laws. It eventually leads to a theory, which is a unifying explanation of a set of facts and laws. And of course, from the theories, you can now generate further observations and further discoveries. Now, what exactly is a scientific model? A scientific model explains how nature operates. It's always grounded or based on observations or experimentation, and it simplifies and categorizes and connects these different observations into one unifying idea. It has to be sensible, meaning that you can't say Martians came down and took away something and that explains things. It has to be reasonable and sensible. But as with all models, it's limited. And one of the things that science is always doing is exploring models such as plate tectonics or exploring models of how the atom works, and it further refines those models. So we're going to now take a look at the history of the atomic theory or atomic model, because it illustrates these ideas very nicely. It will show you that there's a cumulative aspect of science, and that as a model got developed, say by John Dalton, or a model was developed by Ernest Rutherford, along the way, there are limitations to it. And scientists take those models and further modify them with more complex experiments. The scientific theories are the best explanations at the time, and they're powerful. They make nice predictions, but as always, they undergo more review, and they get modified as more insights modify them further. So we begin with the doctrine of atomism. And the doctrine of atomism was first put together by Lepidus and by Democritus. Both were Greek philosophers. And what they stated was that the natural world consists of two fundamental principles. And those are that it's made up of these things they called atoms, which are indivisible bodies. And between the atoms there is nothing. There is nothing but a void. The word atomus comes from not cuttable. It's indestructible and immutable. Apparently, Democritus came up with an initial idea when he was in a villa, saw a clay pot fall from a second story and shatter on the floor. And he began to think whether you could take those shattered pieces and further divide them, and take those pieces and further divide them, and divide them infinitely till it's infinitely small. And Democritus ultimately rejected that idea and said that at some point you cannot divide the material any smaller. And that's what he suggested was the idea of an atom. He did not do experiments to prove this, but rather proposed it from a philosophical perspective. Now they said that there was an infinite variety of forms, and what that simply meant was that these various atoms that were extremely small moved around through this empty space that was between them, since it wasn't anything smaller than an atom itself. Now they suggested that these small individual atoms could in fact cluster together, and the clusters gave rise to substances, which in the case of Democritus felt could be assembled to make a pot in a Greek villa. Now, Democritus went on to write that nothing exists except atoms and empty space, and everything else is simply an opinion. And it's interesting that he, in fact, was correct on this. So, for centuries went by, we went through a period of alchemists who further studied and looked at what matter is made up, and they began in the 12th, 13th century. They, if you imagine, had the Dumbledore hat on, and they did these odd experiments, and they began to show that, in fact, the existence of the atoms was probably accurate. But it was John Dalton who eventually put together a real solid working model of what atoms were all about. It became known as Dalton's atomic theory. He was an Englishman. He actually enjoyed studying the weather, and from his studies of the weather and how gases behaved, he put together the atomic theory. What that meant was that elements are made up of atoms, which were the Democritus atoms of centuries before. Atoms of each element are identical. And if you take a look at one element, such as carbon, and say looked at another material like iron, the atoms that make up the carbon substance, like coal, and the atoms that make up iron metal, those atoms are different from each other. And because the atoms are different from each other, then the element or collection of things such as the coal or such as the iron metal, that's what makes them different. It's the atoms that are different that make that material different. And in a lump of coal or in a iron bar, all of the atoms are the same in there. Therefore, there were iron atoms or carbon atoms. He went on to suggest that, in fact, atoms are able to combine with each other. And when they combine, you could make a different substance. For example, water. Water was a compound and it was created by, or it occurs by linking different atoms together. In that case, he actually knew it was oxygen and hydrogen atoms that combined together to make this substance called water. But what's interesting is he said that each compound, in this case water, always had a specific number and kinds of atoms. And he was able to show that, in fact, water was 2 hydrogen atoms and 1 oxygen atom. And that all water had this combination. There were always 2 hydrogens and 1 oxygen, and you could not have any other ratio of those atoms. And if you did, it no longer was that same substance. You would no longer have water. He also went on to say that what went on in a chemical reaction was a rearrangement of the atoms themselves. The atoms don't change, so in the case of water, if you split water into oxygen gas and hydrogen gas, the atoms themselves are still the same. You don't create new atoms or wipe out new atoms. In fact, you are simply rearranging these atoms, and that's what made up a chemical reaction. He went on to state the first description of what he thought atoms themselves were about, and they were simply solid spheres, and that's what an atom was made. It's called a spherical model. Now, the description above of what elements are made up of and what chemical reactions, he got that spot on. He got that almost perfect, which is rather remarkable given the time period he lived in. But the notion that the atoms themselves are solid spheres, that description was not correct. But with the data at the time, it did work and it did fit the observations that were known. This is from his notebooks, and you could see how he had symbols for the elements. The circle and the dot was hydrogen, and the black filled-in item was carbon. You can also see on the right side that he was indicating that atoms could combine with each other and make compounds. And he again suggested that these atoms connected to each other in very specific ratios, such as water is 2 to 1, hydrogen to oxygen. So he went on to state that matter, though divisible, is in an extreme degree, is never left not infinitely divisible. And of course that goes back to Democritus. That is, there must be some point beyond which we cannot go in the division of matter. And I've chosen the word atom to signify these ultimate particles. Notice he builds off of Democritus's original description of them, but really creates a much more robust description describing how atoms can in fact connect together to form compounds, and that the elements are all made up of the same kind of atom. It's a much more robust and very accurate and powerful model that John Dalton gives us. So John Dalton in 1803 suggests the spherical model of the atom. Now, what happens in 1869 is a Russian by the name of Mendeleev comes along and says that in a dream, he indicates, there was a table and all the elements fell into place as required. And upon awakening, I immediately wrote it down on a piece of paper. And of course what he did was he put these atoms, these different kinds of atoms, in an organized structure called the periodic table. So this is how he puts it together. There were 63 known elements, known atoms, at the time of Mendeleev, and he wanted to organize them. And what he did was he put them in columns, and those columns were assembled because they had similar properties. So the atoms within the first column, for example, which was lithium and sodium and potassium, that column, they were all very, very reactive with water. And because they were, Mendeleev felt they belonged in that same column or grouping. Then what he did was he then arranged them horizontally based upon increasing weight. And Independently, a German by the name of Lothar Meyer actually developed a similar idea. Now, Mendeleev's big success in saying that his arrangement of these different atoms was correct was he was able to predict that there were certain elements or atoms that had not been discovered yet. And these atoms that were missing, he could predict what they would be like chemically. Notice here that you have a scientific model, which is the periodic table. The periodic table is a model of the organization of elements or atoms, and that model allowed for predictions about things that had not happened yet. And when in fact they discovered and found those atoms, sure enough, they matched the properties he predicted. And that supporting evidence or predictions is a very powerful support for any model. And of course, this is the basis for the periodic table that we've worked with so carefully. And here again is the original one that was published in 1872 by Mendeleev. And you'll notice vertically lithium and sodium and potassium and rubidium, those are all vertically linked together. And then he has beryllium and magnesium and calcium and zinc, and those all link up together very, very nicely. You'll notice that some, as you go lower down, are placed into that same group that ultimately are not there. And that is because he didn't know the existence of the transition elements. But the first about 3 or 4 lines, that grouping was spot on. Now, here what we were addressing is the layout that Mendeleev was putting together. And what you'll notice is that at the time there was a missing number 68, which is gallium, because that was its weight. And then a weight of 72 was germanium. And as you can see on the left, that the gallium with the weight of 68, on the look below, that Mendeleev that predicted that the atomic mass should be such and such, the melting point would be low, the density would be 5.9, etc., etc. And in fact, when they discovered gallium, you could see just how close his numbers came to that. And then germanium, Mendeleev predicted the atomic mass would be about 72 AMUs. The density would be 5.5. And in fact, again, when they discover it, you can see how powerful that prediction was for him. So when the remaining elements were discovered, and you get a nice color code here, you could see that it really did fill in gaps that were created by Mendeleev's original model. And again, notice the power of predictability. He was able to predict items that had not yet been discovered, and that again was very good evidence for his model. Now I'm going to stop it here so that this video doesn't get too long, and I'm going to pick it up with part 2 with the discovery of the electron.